Okay, since I have known about we have known about stream function, velocity, potential, then different flow of movement, we will going to discuss about fluid flow equations and dive little bit into the fluid dynamics. Okay, fluid flow equations. So we have the rate of fluid flow. Rate of fluid flow. What is the rate of fluid flow? It is a quantity of fluid per unit time. Quantity of fluid per unit time. And the quantity is weight for compressible fluid, and it is volume for incompressible fluid. That is for incompressible fluid, the rate is denoted by q, and q is a times velocity of fluid, and a times v is the rate of volume flowing through, flowing per unit time. Now we have our continuity equations. We have continuity equation. What is continuity equation? Continuity equation is based on conservation of mass. That is, suppose there is a channel, there is a section 1 and section 2. The area of section 1 is a1, area of section 2 is a2. Then conservation of mass states that the rate of mass flowing through one channel, section 1, is equals to rate flowing through section 2. So if I diagnose, it is density times velocity volume rate. Yeah, density times q1 times density times q2. So it is q1 equals to q2, and volume flow rate is a1 v1 velocity and a2 v2. Hence this is our continuity equation for the flow, for the diverging flow. But if I want to make a small particle, the differential element, use differential element to derive the continuity equation, then it looks like this: x y z. This is 0, this is our element, and this the dimension is dx dy dz of this small element, and this section that I've marked, and these sections are x inflow and x outflow. We are taking one dimensional case only. So here I have mass in is rho, u is the velocity, inlet velocity, and dy dz is the cross section area. This is dy and this is dz. And uh, if I calculate m out, it is same: rho plus u, rho times u times dy dz plus small change in, I have to differentiate this with respect to x, which gives me dy dx of rho u dy dz whole dx. From this m in and m out, I have the gain in mass as, if I subtract m out and m in, I get negative, sorry, m in minus m out, I get the negative of dy dx times rho u times dx dy dz. Yet this gain in mass is in 1D, one dimensional flow, but in 3D I have the gain in mass of minus d by dy rho u dx dy dz n minus dy dz, sorry, rho v rho w dx dy dz. So this is our gain in mass in 3D. So according to mass conservation, the gain in mass must be equal to change in mass, gain in mass, that is if I take a d by dx negative dx dy dz. Okay, sorry, I cannot do this. This is mathematically incorrect. However, du by dx plus dv by dy plus dw by dz times rho dx dy dz. If rho is constant, the flow is incompressible and it doesn't change with space. Dx dy dz, then it should be equals to d of m upon dt. So here d of m upon dt converts like uh, d rho density times small element volume of small element by dt. So here this occurs, and since these dx dy dz are doesn't depend on time t, so only density is dependent on time t. Since it is an incompressible flow that we have considered, it becomes zero. So our equation becomes, so these all become zero, cancelled away, and du upon dx minus is left here, plus dv upon dy plus dw upon dz equals to 0 is the continuity equation in differential form. Okay, so if I put from the velocity potential and stream function, if I put u equals to in 2D flow, u and v, and this equation for in continuity equation du upon dx plus dv upon dy equals to 0. In this equation I'll get equation something like so this is a continuity equation. Here z component is 0, so I have not considered dw upon dz. And if I consider this, I'll get something like d square x plus d square okay, so d square xi plus dx square plus d square xi plus dy square equals to 0. It sorry, here this is known as Laplace equation. Laplace equation. Okay. uh, Similarly, in case of stream function, I'll get something like this d square xi by dx square plus d square xi by dy square equals to 0. So it is for irrotational flows. Irrotational flows. Why irrotational flows? Because the rotational component is omega z 1 by 2 dv upon dx minus du upon dy. So I put these values into this equation and it gives me this form. And if this is 0, then this means omega z is 0. If omega z is 0, then rotational component is 0. It means irrotational flow. Okay. Now, now we will talk about the dynamics in later fluid dynamics in later videos.